next example of a modern PRV we will review is the Anderson Greenwood 80 series and the Rosemount 708 acoustic transmitter. The Rosemount acoustic transmitter is affixed to the PRV's outlet piping and measures sound levels in the pipe that occur with a valve opening or closing, as well as any temperature change due to flow during an overpressure event. The transmitter will provide time-stamped notification when the release is occurring and when the release has stopped. The Rosemount acoustic monitor is non-intrusive and can be directly mounted to piping without the need for cutting or changing piping, and provides for a flexible and easy installation. Illustrated in this graph is a real-time example of an overpressure event on a system using a pressure relief valve with an acoustic transmitter. On the vertical axis, you will see the system pressure referenced by a blue line, the temperature referenced by a green line, and the transmitter's acoustic count indicated in red. The horizontal axis represents time elapsed. Starting at the 10:17 time mark, you will begin to see a gradual increase in the system pressure as indicated by the blue line moving up. At this point, the pressure is below the relief valve set point of 60 psi and the valve is containing the increased pressure. The valve remains closed and is indicated by the zero data count in red from the acoustic transmitter. Approximately 40 seconds later, the system pressure begins to increase further, and as it reaches the valve set pressure and begins to lift, the acoustic count begins to increase. As the event is ending, the system pressure decreases as well as the acoustic signal count, and the system reaches a safe and steady state with the valve closed and the system pressure normalized. Reviewing the acoustic signal in red, we can see the rapid increase and decrease in acoustic counts during the event. This rapid change in acoustic signal indicates the valve is chattering as it opened and closed rapidly. Chattering of a relief valve can be damaging to seating surfaces and can be due to excessive inlet line losses or a valve with incorrectly adjusted blowdown. In another example of an acoustic monitored pressure relief valve, we can see a much cleaner and more distinct acoustic signal count line. In this graph, we can see that as the system pressure increases, the relief valve begins to simmer prior to opening, as indicated by the small acoustic signal count. But in this case, as system pressure increases, the valve opens and attains full lift and remains open until the system pressure drops below its set point, where the valve closes almost immediately. In this case, no chattering of the valve occurred and the valve quickly returned to protecting the system.